The next talk is by Amnon Geifman Meirav Galun, David Jacobs, and Ronen Basri from Weizmann. It's on the spectral bias of convolutional neural tangent and Gaussian process kernels.
So hi, my name is Amnon, and I'll talk about our work on the spectral bias of convolutional neural tangent and Gaussian process kernel. This is a joint work with Meirav Galun, David Jacobs, and Ronen Basri. We all know that deep learning is considered to be a great success, but actually, it was convolutional network that really began the deep learning revolution. The thing is that there is still no widely accepted explanation of why CNN are so successful. In our work, we try to give a theoretical explanation of the success of convolutional network based on their corresponding neural tangent kernel. Let's start with some toy example to illustrate what kind of phenomena we are about to explain. Consider the following experiment. We use a convolutional network to map random noise input to a given image. Here we construct the input from two identical noise patterns, where the second pattern is further contaminated by Gaussian noise. We use the parameter V to control the variance of the added noise. The goal of this experiment is to check how hard it will be for the network to overfit the target image for different values of V. Interestingly, if this additional noise is small, the network will be very slow to learn the mapping, while if the additional noise is large, the network will learn the mapping much faster. This can be seen by the result in this slide, which were obtained after 150 iterations. The fit shown on the left, which was obtained with small additional noise, is poor, while with large noise, the same number of iterations, a near-perfect fit is obtained on the right. This example is evidence of the inductive bias of CNN. Our aim in this talk is to characterize this inductive bias. We will explain later in this talk how our theory explains this example. Our work builds upon theory of neural tangent kernel. We denote the network by f of input x and weight theta. Previous work has shown that when we train a convolutional network with large number of channels, and if the weights are initial slow to 0, then the weights at convergence remain close to their initial value. This implies that the first-order Taylor approximation with respect to the weights describe the network well. It means that when we optimize the MSC loss with gradient descent, the loss evolves exponentially with t, the number of iteration, and depend on an application of iteration metrics to the power of t applied to the label of the training set denoted here by y. The iteration matrix is the identity minus learning rate eta times k. This matrix k is also known as the anti-k matrix. Its components are the inner product of the gradients of the network of all pair of training samples. Roughly speaking, this follows from the linearity of the Taylor approximation. A consequence of this theory is that the speed of convergence of gradient descent is fully characterized by the spectrum of the kernel matrix K. In our work, we characterize the spectrum of K to analyze which target functions are easier to learn and which one are harder. A good starting point for this discussion is some previous works performed in our lab that showed that fully connected network first learn low frequency in the target function and only later fits the higher frequency. This has several practical implications. The most noticeable one is in positional encoding in NERF, where this theory was used to enable the network to learn high frequency in the image. So back to our problem. We want to determine the speed of convergence of CNN for learning different target functions. From previous slides, we saw that a good way of doing that is characterizing the eigenvalues and eigenvectors of the matrix K. Following our previous slide, the eigenvector of K will give us the direction of convergence. The corresponding eigenvalue will be inversely proportional to the speed of convergence in this direction. The matrix K and its spectrum depend on the data. Therefore, in order to be able to identify its spectrum, we must assume some distribution of the data. For simplicity, we use multi-channel input data, for example, RGB images, where we assume that each pixel is sampled uniformly from the sphere. In general, we can deal with any number of input channels with higher dimensional spheres. We start with the eigenvector. In our paper, we show that the kth eigenvector of the kernel matrix satisfy that each component in this vector is a function of an input image, where this function takes the form of product of Fourier component applied on each pixel separately. When the input pixel is on the circle, meaning that each pixel has only two channels, fkj are the standard Fourier functions on the circle of frequency kj. If the pixel contains 3 or more input channels, fkj's are the spherical harmonic functions. Here, xi is the ith image in the training set, and the upper script refer to a specific pixel in this image. The mathematical form of the eigenvector might be a bit intimidating, so let's see how vk looks like. It is composed of a concatenation of a function applied on each example in the dataset. If we zoom in, for example, into the second entry of this vector, we can see that the function fk operates on the image x2. Specifically, this function takes the input image, separates it into different pixels. On each pixel, it applies a Fourier component of different frequency, and the function itself is then a product of all these frequencies. Now that we have the direction of convergence, we can talk about the speed of convergence in this direction. The eigenvalue of the kth eigenvector vk is a product of two terms. The term on the right is a product of the different frequencies ki in the different pixels, raised to a power that is proportional to the number of input channels. This term implies that high frequency are slower to learn than low frequency pixel-wise. The term on the left is roughly a constant. That depends on the architecture. It depends on the number of paths in the computational graph of the network from each input pixel in the image to the output of the networks. This constant grows exponentially with the number of paths, giving a high weight to nearby pixels and low weight for pixels that are far apart. Now we can have some example to illustrate what convnets are biased towards. Assuming our target function takes the following form, meaning it is a product of Fourier component, each is applied on different pixels of the image. On a side note, I'll say that a general target function can be expressed as a linear combination of such simple functions. It is important not to be confused here. We are interested in the decomposition of the target function into Fourier basis and not in the Fourier transform of the image. What we aim to do in the next 3 slides is, given the different ki, we will rank the target function according to the time of convergence predicted by our theory. We will start with what we call low-frequency bias in CNNs. Here is a basic example where a target function is generated by fk, which are all low-frequency functions. Just to make sure we are on the same page, this schematic figure means that we take the image of the cat, break it into its different pixels. On the first pixel, we apply a Fourier function that looks like this. On the second, we apply this function, and so on. The target function is then the product of all these functions. Now we can see another kind of target function. This function is the same, but with higher frequency in the center pixel, and therefore it is harder for the network to learn. And as we increase the frequency in this pixel, the target function becomes harder for the network to learn. This is a result of the right-hand side of our eigenvalue characterization. In the same spirit, here is another example of a target function. This one is harder for the network to learn because the high frequency are spread across more pixels. And this one is even harder because the high frequency are spread on even more pixels. This is also a result of the right-hand side of our eigenvalue characterization. The last bias is locality bias. It says that the network is biased to learn nearby pixels as opposed to faraway pixels. Here is the basic example where the target function contains high frequency in 2 pixels. Here is a harder example, since the target function is the same, but the high frequencies are now located on pixels that are farther from each other. And this one is even harder since the high frequency are even farther. This is a result of the dependency of the eigenvalue in the architecture. Now we are ready to go back to our toy example. What actually happened here is that we used two copies of the same white noise, and the target function, which is the pixel value, is the same in the two cases. What it means is that if the target function of the large noise looked like this in a rough 1D projection, then the target function in the small-headed noise looks like this, meaning that now the network needs to produce high difference in the output value with small difference in the input space. In the context of our theory, this means that if we want to interpolate the point with a Fourier component, the low noise case will need a higher frequency function, and the high noise case will need a low frequency function. Our theory predicts that this higher frequency will be harder to learn. So to conclude, we analyzed the spectral bias of CNN. The eigenvectors are a product of Fourier components. The eigenvalue decay polynomially for each pixel separately, give greater weights to high frequency in nearby pixels, and decay slower when only a few pixels are considered. In the paper, we extended to various other types of architecture and for ResNet in a follow-up work. Thank you.
Questions? So let me ask you a question.
Right.
In terms of, can I take these theoretical results and change my training set in order to get better training?
So I guess you can. So the theory actually holds in practice in some cases. I guess you can do it, but it will not be so trivial. We need to think about it, yeah.
Okay. The lights are up, so you can ask questions. No more questions. Okay. Thank you.
Thank you.